Hello everyone, my name is Karen Leopoldino and I will present a part of my dissertation that I developed as a visiting scholar at the School of Geoscience at the University of Oklahoma. The title is Unsupervised Machine Learning Applied to Seismic Characterization and Deep Water Elements Identification in Ceara Basin, Brazil. Dr. Heather Biddle was my advisor. This is the outline that is divided into these topics, where in the introduction I will talk about the main motivation of this work, then the dataset available, after the methodology that we choose in this project, and finally the results and conclusions. So, the Equatorial Atlantic basins has been the focus of considerable interest due to the large hydrocarbon discoveries within transfer basins of West Africa, including the large oil fields in Ghana, Ivory Coast, also in Guyana, Suriname, and French Guiana. However, studies on the tectonic regimes associated with transfer margins in their evolution, structures, and petroleum potential are scarce, partially due to the geological complexity of this area. The Brazilian equatorial margin is composed by 5 sedimentary basins along the coast. It is comprised by the Foz do Amazonas, Pará-Maranhão, Barreirinhas, Ceará, and Potiguar basins. The deep water of the Brazilian equatorial margin is underexplored and only a few wells have been drilled. However, available public domain data from ongoing seismic evaluation in the region suggest that there is a high potential for light oil discoveries in the Upper Cretaceous turbidite sandstone reservoirs in stratigraphic traps. So, all this margin is considered as a frontier basins. This study is based on a 3D seismic dataset in addition to 3 exploration wells drilled for the oil industry between 2012 and 2013. The seismic survey was acquired in 2003 by CGG and covers a large area of the deep water of Ceara Basin. The seismic cube was cropped and covers an area of 765 kilometers square, and also the cube was cropped vertically according to our area of interest. The 3 exploration wells include a suite of line logs and drilling reports. The borehole dataset consists of shallow and deep resistivity curves, the gamma ray log, corrected density, and neutron porosity. Most of the geological information is provided by cuttings and sidewall core sample description in well history reports, supplemented by borehole logs. All this data was supplied by the Brazilian National Agency of Oil, Gas, and Biofuels. This is the flowchart summarizing the methodology used in this work. We used conventional seismic data interpretation techniques, 3D seismic attributes, and unsupervised machine learning techniques to investigate the seismic geomorphology and the depositional environment within the Albian to Turonian age interval. First, horizons were mapped and gridded to produce continuous surface. Then, the 3D seismic dataset was cropped between these 2 horizons. A seismic geomorphology workflow was used to highlight structural and architectural elements by means of attributes analysis and well log interpretation, as well as the sedimentary deposition at that time. In this presentation, we will highlight the results of the unsupervised machine learning techniques. Once a presentation about the seismic attributes analysis was recorded and presented in a previous geoscience conference. Please, if you are curious about the seismic attributes analysis, see this presentation in the AASPI website. Here, we present how different attributes highlight different features of interest as combined them using multi-attributes analysis techniques, providing a mean to better characterize geological features. This is the Ceara Basin litho and chronostratigraphic columns with the correlation panel amongst 3D seismic reflectors and the stratigraphic information from the Albian to Turonian age in this basin. Here, the 3D seismic cropped showing the crossline 2251 and the canoa quebrada well. Above, it is displayed the original seismic cube, and below is shown the flattened seismic cube. In the right side is presented the crossline 2320 and the location of the 4 phantom horizons interpreted. The phantom horizon 1 is the youngest and near the Turonian top, and the phantom horizon 4 is the oldest and near the Albian base. As you can see, the Albian to Turonian interval consists in part of strong continuous reflectors incised by discontinuous reflectors with variable reflectivity. So, multi-attributes analysis is laborious and time-consuming. So, to enhance this analysis, we chose to explore unsupervised machine learning methods to better characterize seismic facies within deep water channels. The attributes used in the machine learning algorithms were chosen based on the Roden and Sacre list of common seismic attributes and the type and the interpretative use. To better evaluate the seismic facies, we employed self-organizing maps, SOM, and independent component analysis (ICA) algorithms to define the facies. The SOM is an unsupervised machine learning technique that is frequently used in many areas to find patterns with similar characteristics within their respective datasets. The ICA approach is related to projection pursuit, which is a statistical technique for finding interesting projections of multidimensional data. In turn, such projections are useful for optimal data visualization. This technique is considered as an extension of principal component analysis, and it assumes that the signal has a non-Gaussian distribution. So, we chose this technique to reduce the multiplicity of spectral data and enhance the most energetic trends inside the data that can be visualized using the 3 primary colors of red, green, and blue. In this study, we used this algorithm to extract the spectral response that can better delineate seismic features associated with different geologic features. So, 14 spectral magnitude components from 5 to 70 Hz attributes were used as inputs. This approach has been used in seismic analysis of carbonates as the Buene collaborators work, as well as fluvial dactylic system as another collaborators work, and in turbidite channels as Lubo and Robles and Mafurt work. For the SOM attribute inputs, we use RMS amplitude, coherence energy, instantaneous frequency, GLCM homogeneity, and also spectral magnitude component of 30 Hz. And as you can see in these attributes, the geological features are easily seen. For example, channel complex, minor channels here, also the bifurcation and distributaries, some depot centers here, faults, also feeder channels in these locations. A fan-like structure is easily seen at this point here, also associated with faults. Point bars in some location of the channel complex, dendritic lobes, and smaller channels. This figure shows the 4 phantom horizon illustrating the distribution of the seismic geomorphology, and in the upslope here, the architectural elements are not well defined. For example, the feeder channels here, whilst the geomorphology close the amontado well in this location is also not well characterized. A vertical slice is shown with our SOM classification. From this classification, we can observe three distinctive colors or phases. The green colors represent the continuous high amplitude phases, and the brightest green represent the seismic reflector with a high impedance contrast. Comparing the results of the well phases, these colors are associated with a metric interpreted with sandstones and shales, more sand than shale, as you can see here. And the purple colors are representative of the chaotic moderate amplitude phases. So this figure shows that the purple colors are associated with a subtle interpreted shales and sandstones, more shale than sandstone. And the blue colors represent the weaker reflections that are more representative in the upslope portion, as you can see here in this figure, these comparative figures. The first figure displays the results of the independent component 1 along the phantom horizon 3. The IC1 results reveals the same deep water elements previously seen in the SOM analysis. However, we note that ICA1 presents less noise and geological faults that are well defined and delineated and clearer than the SOM results. Moreover, the channel complex, smaller channels, faults, depot centers, point bars, and feeder channels are well delineated and internally resolvable in the ICA1 than the others ICAs. In addition, the channel that bifurcates into three distributary channels towards the northwest is better delineated and internally resolved in the ICA1. The second one displays independent component 2 with more clearly images of the large-scale geological features such as the channel complex, the depot centers, and smaller channels. The distributary channels are visible but are difficult to delineate using the ICA2. Faults are also well imaged when compared to the SM results. And as seen in ICA1, ICA2, there are less noise than the SOM. The third figure for independent component 3 still exhibits the large-scale geological features such as the channel complex, depot centers, and smaller channels. However, the smaller scale geological features such as faults and feeder channels are less apparent with the independent component 3 than on ICA1 and ICA2. Although we can delineate the smaller channel, its bifurcation into three distributary channels is difficult to interpret in the ICA3. The independent component 3 better reveals the large-scale geological features such as the channel complex, depot centers, and smaller channels and faults. However, the channel complex is not internally well resolved as it has poor internal delineation when compared with the ICA1, ICA2, and ICA3. It's because of that we chose the ICA1, ICA2, and ICA3 to visualize these results. Use the primary red, green, and blue colors. In general, the channel complex is characterized predominantly by green facies intercalated with some yellow and purple seismic facies, whereas the area close to the Basin well has predominantly purple facies. At the fatal horizon 1, the channel complex has predominantly green facies and purple facies. The smaller channel in the northwest has predominantly yellow seismic facies when compared to the older older horizons. At the fatal horizon 3, this one, the geological features close to the Amontado well here is predominantly characterized by green and purple seismic facies, whereas the dendritic lobe here has yellow seismic facies. These dendritic lobes appears to feed the smaller channels, and this channel has the same seismic facies as its distributaries. The channel complex has a greater variability of seismic facies and is well delineated. At the fatal horizon 4, the channel complex has a high variability of seismic facies. However, its shape is not well defined and appears similar to braided channels. Also, the fan-like structure here is highly variable with a mix of different seismic facies, and the variability of which was better seen using ICA than SIM attributes analysis. So, as you can see, the upslope it's also better visualized and analyzed using the ICA than SIM results. It's possible to see the feeder channels here in the upslope, also faults, and the variability of the seismic facies in all the deep water elements. To validate our interpretation of the seismic facies using principles of geomorphology and the ICA-RGB blending to highlight the different architectural elements, we relate the seismic facies with the lithologies analyzing the facies information from the Canoa Quebrada well report. So, these figures demonstrate that the sandstones probably associated with sheet sands correlates with a mixture of bright yellow with green seismic facies associated with high amplitude and parallel reflectors. The blue and purple facies are associated with an interpreted shale and mudstones, more shale than sand. The main conclusions of this work is that meaningful geological features were successfully extracted from 3D seismic data using unsupervised machine learning techniques. For example, channel complex, point bars, feeder channels, faults, depot centers, dendritic lobes, smaller channels, and distributaries. The integration of the machine learning results with well information helped to identify sand-rich deep water elements. Also, the ICA is a powerful technique to reduce dimensionality, extract valuable information from multiple seismic attributes volumes, and to separate geological features from noise. The ICA provided better resolution than SIM analysis. Lastly, the integration of seismic attributes and machine learning approach is more efficient for identifying the positional patterns than the conventional seismic reflection data, mainly if the interpreter wants a quick overview of the exploration area using a huge 3D seismic cube. Also, These approaches can be applied to other unexplored basins in the equatorial Atlantic margin for both exploration and production purposes. Besides that, it will help to narrow down areas for more detailed manual interpretation. And also, the deep water upslope petroleum potential in stratigraphic traps were emphasized since a fan-like structure and an associated fault was mapped. These types of structures provided large volumes of hydrocarbon in the equatorial Atlantic in the Jubilee field, and it can be an important target for the hydrocarbon exploration of the conjugated Brazilian equatorial margin. So I would like to thank you, the ANP, the Brazilian National Agency of Oil, Gas and Biofuels, the Schlumberger for the Petrol software, and the Research Consortium, AASPI, of the University of Oklahoma. And thank you, audience, for your time and attention.